Hello everyone, this is lecture 12, method of undetermined coefficients. So in this lecture, we would look at a new solutions method to solve for a non-homogeneous equations. More specifically, we will look into a linear second-order differential equation with constant coefficients, but now the forcing term on the right-hand side of the equation is something different from zero. That is, we will look into the equation of the form ay double prime plus by prime plus cy equal to g of t. In this case, a g of t is different from zero. To find the general solution for this type of equations, we will choose a trial solutions, or more specifically, choose a trial particular solutions who forms mirror of the forcing term. That means you look at the forcing term or g of t, and you choose a trial particular solutions that mimic or mirror the forcing term. Then we're going to use that to assemble the general solutions by combining something called homogeneous solutions and particular solutions. And then this is a difficult problem trying to solve a different class of differential equation, and sometimes it's not going to be perfect, and we will learn to recognize when the method failed and find the different approach to solve the problem. And before we get into the method of undetermined coefficients, I have some definitions and theorem to give you, and hopefully this is going to be useful later on in the lecture. So the first definition is called differential operators. So you have seen this type of operator before, right? We just didn't form it that way. Okay, so the symbol capital D is called a differential operator if it transforms a differentiable function into another function. Now, differential operator can be thought of as the first derivative, the second derivative, the third derivative, so on and so forth. Or in multivariable calculus, you can think of D as partial derivative. Then the n-order differential operator is defined as capital L equal to a sub n of x times dn. So dn can be thought as the nth derivative plus a sub n minus 1 of x times d of the n minus 1 derivative, so on and so forth, up to a1x times d for capital D by itself can be the first derivative, plus a0x. So in this definition, you have linear combinations of all the derivatives together. So similar to what we have for the case of differential equations set up like this. So in this case, we have a second order differential equations, or the linear combinations of the second derivative, the first derivative, and the zero derivative. Now, based on this differential operator, we usually have two basic property of differentiations. The first one is when you apply the differential operator on the constant multiple, then you can pull out the constant and just take the derivative or apply the differential operator on the functions. That is, d apply on the constant multiple of the function f. That is, you can pull out the constant c and just apply the derivative on the function. So in this case, c is a constant. Now you can take this differential operator and apply that on the sum or difference of two functions. So you take d, apply that on the sum of two functions f of x and g of x. So derivative of the sum is the sum of derivative, and that is d apply on the function f plus d apply on the function g of x. Okay. And from these two basic properties of differentiations, you arrive at the differential operator that is linear. This linear differential operator allows you to carry out the calculations based on the linear combinations of functions. So the linear differential operator apply on alpha times f of x plus beta times g of x. So linear differential operator applied on a linear combinations of functions is equal to linear combinations of differential operator. So alpha times L applied on f of x plus beta times L applied on g of x. In this case, alpha and beta are constants. Now let's move on to some definitions, some other definitions. The first definition is the non-homogeneous differential equation. So this is the non-homogeneous differential equations. So the setup is this: the linear second-order differential equations of the form a times y double prime plus b times y prime plus cy equal to g of t. In this case, a, b, and c are constant, and g of t is different from 0. Therefore, this equation is called a homogeneous equation. And the job for the task is always to find the solutions to the differential equations, or eventually we want to solve for the initial value problem. So in this case, so far up to this point, you know how to solve the solutions of a homogeneous differential equation using the method of characteristic. But now the forcing term or the right-hand side is different from 0. What's going to happen? So we still consider the linear non-homogeneous second-order differential equation with constant coefficients of the form ay double prime plus by prime plus cy equal to g of t. Again, g of t is different from 0, a, b, and c are constant. Now, similar to the case of homogeneous equations, let's assume that you have two solutions, and two solutions are linearly independent, or they form a fundamental set of solutions. Then y1 satisfies the differential equations, and y2 has to satisfy the differential equation as well. So that is, you have a times y1 double prime plus by1 prime plus c times y1 equal to g of t. Similarly, you have a times y2 double prime plus b times y2 prime plus c times y2 equal to g of t. And right, so this is the assumptions that you have two solutions, y1 and y2, and they are satisfying the differential equation, this differential equations. And they are also linearly independent. That is, the general solutions can be written as linear combinations of y1 and y2. So that's what we know from the case of homogeneous equations. So y is equal to c1 times y1 plus c2 times y2, where c1 and c2 are arbitrary constants. Okay. With these assumptions, we have a supposed general solution. We can assume that this value of y, or this function y, is also satisfying the differential equations. So that is the differential equation we're talking about. Then what it means is that when you substitute into this general solution into the differential equations, you should have a true statement. That is, the left-hand side equal to the right-hand side. So that's what we're going to do now. Substitute the value of y, or the function y, into the left-hand side of the differential equations, and hopefully you get a true statement out of that. So we're going to substitute y prime and y double prime into the differential equations. So I'm going to take the left-hand side and work with it. So ay double prime plus by prime plus cy. So a times c1 y1 plus c2 y2, take second derivative of this, plus b times c1 y1 plus c2 y2, take the first derivative, plus c times c1 y1 plus c2 y2. So derivative of a constant multiple, or the linear combinations of y1 and y2, derivative of the sum is sum of derivative, and you take derivative of the constant multiple. That is, you can just take the constant out of the integral of the derivative operator, and just take derivative on the function y1 and y2. So this gives me a times c1 y1 double prime plus c2 y2 double prime, plus b times c1 y1 prime plus c2 y2 prime, plus c times c1 y1 plus c2 y2. Okay. What we are trying to do here, again, we try to substitute the function y into the differential equations, or the left-hand side of the differential equations, and hopefully you get a true statement out of these calculations. So next up, we're going to distribute a into the parenthesis, b into the parenthesis, and c into the parenthesis, and see what we get. So I get a times c1 y1 double prime plus a times c2 y2 double prime plus b times c1 y1 prime plus b times c2 y2 prime plus c times c1 y1 plus c times c2 y2. Alright. So if you notice, you have three terms that has the constant c1. So we're going to take c1 as a common factor. So c1 is a common factor, and you're left with a times y1 double prime plus b times y1 prime plus c times y1. And also we have three terms with c2 as a common factor. So you pull out c2, and you're left with a times y2 double prime plus b times y2 prime plus c times y2. And we make an assumption earlier that y1 and y2 are two solutions of the non-homogeneous equations. That is, when you plug in y1 for the differential equation, this is what you get. And when you substitute y2 into the functions, into the equation, this is what you get. So this part of the expressions right here is equal to g of t, based on this first equations. And from the second equations, it gives you this part to be g of t. So you have c1 times g of t plus c2 times g of t, and g of t is the common factor in this case, and so you're left with c1 plus c2 times g of t. So we make an assumptions on the general solutions, that is the linear combination of c1 of y1 and y2. We make that assumption. We want to check if that is the case, if that linear combination is also a solutions to differential equations. And so we substitute this into the left-hand side of the differential equations, and hopefully we get g of t by itself. However, the result gives you c1 plus c2 times g of t. And of course, there are some cases where c1 plus c2 equal to 1 and the right-hand side do equal to g of t. However, that's not a general case. Right? So in practice, it's not going to always happen that c1 plus c2 equal to 1. And so we can claim that this is totally different from g of t. So that means that the assumptions that we make, that the general solution is a linear combination of y1 and y2, is no longer valid. So let me claim that here. So this shows that y does not satisfy the non-homogeneous differential equations. Thus, we need to look at a different approach. To find general solutions. So because of this class of differential equations, that we run into this problem. And to resolve this problem, we're going to look at two different methods, one in this lecture 12 and another one in lecture 13. So in lecture 12, we're going to look at undetermined coefficients, and in lecture 13, we talk about variations of parameters. Okay. Now, before we dive into the particular method of undetermined coefficients, we look at the type of solutions for the non-homogeneous equations that we're going to encounter. So again, we're going to look at non-homogeneous second-order or linear non-homogeneous second-order differential equations with constant coefficients of the form ay double prime plus by prime plus cy equal to g of t. In this case, g of t is different from 0. So the general solutions of non-homogeneous equation can be written in the form of y equal to c1 y1 plus c2 y2 plus something new here, and y sub p is called, in this context, a particular solutions. So this is different from the particular solutions when we solve for c1 and c2 when you use the initial conditions. So please be careful here. There's two solutions added in this general solution. The first part, c1y1 plus c2y2, is called a homogeneous solutions, and so this is the homogeneous solutions, and y sub p is called the particular solutions. And this particular solutions will base on the right-hand side of the differential equations. And the particular solution that we have been talking about is the solution where you need to use the initial conditions to find the arbitrary constants. So those two have different definitions, even though they use the same name. So here I want to note that this is called the homogeneous solutions, and this y sub p is called the particular solutions. Okay. where y1 and y2 are fundamental set of solutions of the corresponding homogeneous equations. So from this differential equations, the corresponding homogeneous equation is that the right-hand side is equal to 0. So we have a y double prime plus by prime plus c times y equal to 0. And y sub p is some particular solutions of the non-homogeneous equations. Okay, so why this combination stuff? We're going to go back and use the notations of the linear differential operator, right? So you have a homogeneous equations, and so that you can produce the homogeneous solutions, okay? And then you add that with a particular solutions to encounter the solution for the non-homogeneous equations. Okay, so now for the linear differential operator, when you apply that on the homogeneous solution, so y sub h is for the homogeneous solutions, you're going to get the right-hand side to be equal to 0. So in this case, y sub h is the homogeneous solutions. Oh, there's another name for this, it's the complementary solutions. Oh, so the linear differential operator applied on the homogeneous solutions give you the right-hand side to be equal to 0. So that is when you substitute y sub h into the left-hand side here, you will obtain the result of 0. Now for y sub p, we say that y sub p is some particular solution of the non-homogeneous equation. That is when you apply the linear operator, differential operator on y sub p, you're going to get g of t, for g of t is different from 0. In other words, when y sub p is a solution to a non-homogeneous equation, then you substitute back into the left-hand side of the equations, then you have the result to be equal to g of t. Now, why the combinations of these two solutions though? So the linear differential operator apply on the sum of the homogeneous solutions and the particular solutions. Right, so the linear differential operator apply on the sum is the sum of the linear differential operator. The linear operator apply on the homogeneous solutions give you 0, and linear differential operator apply on the particular solutions give you g of t, and this is also equal to g of t. And therefore, you have the homogeneous solution, you have the particular solutions, and the combination of the two solutions will give you g of t. Therefore, y sub h plus y sub p is also a solution to the non-homogeneous equations. Thus, y sub h plus y sub p is a solution to the non-homogeneous differential equations. Okay. So again, to the general solutions of the non-homogeneous equations will be the combinations or the sum of the homogeneous solutions and the particular solutions. For a homogeneous solution, at this point you know how to solve for that, right? So you consider the corresponding homogeneous equations, and you can use the method of characteristic to find the roots and then to find the solution of the homogeneous equations. Then we're going to find the particular solutions, and how we find the particular solutions, then we turn to the method of undetermined coefficients or variations of parameter. Okay. So to solve for the non-homogeneous equations, the procedure is as follows. So this is kind of the higher level of information. There's a finer details when we dive into each method to find the particular solutions. But the overall idea is that given the non-homogeneous differential equations, the first thing you need to do is to find homogeneous solutions of the form c1y1 plus c2 times y2 of the corresponding homogeneous equation. Then to find particular solutions y sub p of the non-homogeneous equation. So this is where either you use the method of undetermined coefficients or variations of parameter. And then we're going to form the sum of the homogeneous solutions and the particular solutions to find the general solutions. Okay, so what is the method of undetermined coefficients? The method of undetermined coefficients is that you have to make a trial solutions, and the trial solutions based on the forcing term on the right hand side of the non-homogeneous differential equations. So g of t will have certain form, and the particular solutions will mimic that form of g of t. Okay. But we're gonna dive into the details of method of undetermined coefficients a little bit later, but yeah, I want to give you some of the particular solution form that you may encounter in example and in different problems in this lecture. If the right hand side of g of t has the form of exponential function written in this way, like a times e to the power bt, for a and b are just some constant, then you can make a trial solutions, or you make a guess on the particular solutions by forming a functions of the form capital A times e to the b times t. Well, capital A is a constant that will be determined in the process of undetermined coefficients, right? So that's where the name undetermined coefficients coming from, because you don't know the value of capital A at this point. Little a and little b, of course, are given in the problem. Now, another type of functions that you may encounter is polynomial functions, or in this case, the power functions. When you see a power functions, then you have to make a guess for the particular solution using the entire polynomial functions. So that is, if you have t to the power n, then the guess should be, or the trial solution should be a sub n times t to the power n plus a sub n minus 1 times t to the power n minus 1, so on and so forth, down to a 2 times t squared plus a1 times t plus a0. Okay, where a sub n minus 1, a2, a1, a0 are some constant that will be determined in the process of finding the particular solutions. Again, in this case, a sub n minus 1, a2, a1, a0 are undetermined, and therefore the name undetermined coefficients. Now for sine and cosine, you have to make a guess as the linear combinations of both sine and cosine functions. So if you have a times cosine b of t, the guess should be capital A times cosine of b of t plus capital B times sine b of t. And similarly, for the case of a times sine b of t, then the guess should be capital A times cosine of b of t plus capital B times sine of b of t. So the guess or the trial solution for these two cases are the same. Now, when you have an exponential function multiplied with cosine, the guess should be a times e to the power b times t and cosine of omega t plus capital B times e to the bt times sine of omega t. And for the case of a times e to the bt times sine of omega t, then the guess should be similar or the same as before. So these are the function on the right hand side where it's allowing you to use undetermined coefficients. Okay. If you encounter the right hand side or the forcing terms that is not falling into this category, then you cannot use the undetermined coefficients method to solve the particular solution of non-homogeneous equations. Okay. So what is the procedure here to get the particular solution, or then to find the general solutions of the differential equations? The first step is to find the homogeneous solutions satisfying the homogeneous equations. Right? Then you pick a trial solution y sub p with the same form as the forcing term. Okay, so this is again some of the forcing term that you may encounter. If your trial solution duplicates any term in the homogeneous solutions, multiply it by t to the power k, where k is the smallest possible integer, to avoid forming linear dependency with the homogeneous solutions. So you may encounter this in our problem and in using the undetermined coefficients. So I will show you how that would be and how to resolve it when we go to a specific example. Then you compute, when you know the particular solutions, you compute y sub p prime, y sub p double prime, and then and then substitute them into the non-homogeneous differential equations to solve for the unknown constant, right, or the undetermined coefficients at that point. And then write down the general solution, which is the sum of the homogeneous solutions in the particular solutions. So let's dive into an example here.